Alright, it's Niaki. It's a Niaki osteozone, and today we are going to have the revision of the paper November 2025 A-level chemistry from the Zimsec exam board. So this is the main paper from the November 2025 session, as you can see on the screen, right? So we're going to revise this paper step by step, and if you are doing Zimsec, you need to pay attention to these instructions to the candidates. So we are starting with section A. So for section A, we are required to answer any two questions about this, but for the sake of revision, we are going to answer all the questions, right? So if you haven't checked on our playlist, you need to do so. We are providing massive topical revisions in all the sciences. We have a lot of tutors who specialize in different specialties, so we got you covered in all the sciences, both for the Cambridge and the Zimsec exam board, the O level and the A levels, right? So you must always remember to subscribe, and also whenever you feel like you need our attention, don't hesitate to get in touch so that we can discuss the questions over here for the benefit of others, right? So number one says an organic compound M contains the elements carbon, hydrogen, and then we have oxygen, right? So it contains hydrogen, carbon, and oxygen only. You need also to take note of that one, right? And then it is a relative molecular mass of 86, and then when 0.43 grams of M is burnt in excess oxygen, we are going to have 1.1 grams of carbon dioxide and also 0.45 grams of water. So here we are told that we are going to have excess amount of oxygen, meaning to say this is complete combustion. Are we together? Meaning to say we are going to only have carbon dioxide and water being produced, right? And then here we are given these elements, right? Carbon, hydrogen, and then oxygen, right? And then we are also given the relative molecular mass. So relative molecular mass is defined as the average mass of a molecule measured relative to 1/12 mass of a carbon-12 atom, right? So you should know these definitions by heart. Relative atomic mass, relative formula mass, relative isotopic mass, and etc., right? The Avogadro's law, the Avogadro's constant, right? And also you should be able to differentiate between relative molecular mass and relative formula mass. So relative formula mass is defined as the average mass of one formula unit measured relative to 1/12 mass of a carbon-12 atom, right? So here we are having this relative formula mass in ionic compound, and then this one relative molecular mass in covalent or in molecular compounds. Are we together? So this is the different. This one applies to ionic compounds, and then this one applies to covalent compounds, right? And then the question requires us to define or to deduce the molecular formula, and it is awarded for 5 marks, I mean. So here we don't mainly stick to the given question, but we try to expand the questions so that we can have the full understanding of any related concept within that given radius, right? So here let me clear these underlined facts so that we can have the clear picture of the question, right? So here we are given the MR being equal to 86, and then we are also given the mass of M being equal to 0.43, and then we are also given that the mass of our carbon dioxide is equal to 1.10 grams, and then we are also given that the mass of water is equal to 0.445 grams, right? So we want to deduce the molecular formula. Here we are given the relative molecular mass. So we can first start by deducing the empirical formula, right? So we can start by having the empirical formula, and then from there we can have the molecular formula, right? So for us, we are told that the element contains carbon, hydrogen, and then oxygen only, right? So here we are given the mass of carbon dioxide. This simply means to say we can calculate the number of moles of carbon, right? So here we start by calculating the number of moles of carbon dioxide. So N, so you must always remember this chief equation in stoichiometry. N is equals to mass over MR, right? So here we're given the mass being equal to 1.1, and then the MR is equal to 44. So I'm simply going to punch this straight to a calculator. So it's 1.1 divided by 44, and then we are going to have 0.025 number of moles, right? 0.025 moles, right? And then here we have this 1 mole of carbon dioxide. So 1 mole of carbon dioxide contains 1 mole of carbon atom, right? So here we have 1 mole being equal to 1 mole. This simply mean to say this number of moles, 0.025, is also equal to 0.25. So these are the number of moles of carbon atom. And then the mass, we go back to this chief equation again. To have the mass, we need to multiply N by MR to have the mass. So here we have this number of moles multiplied by the AR. So here we are having atomic masses, right? So it's AR of carbon, which is equal to 12. So we multiply this one by 12 to have the mass of carbon, right? So what we want to have is the mass of carbon, so that we can go on to calculate the empirical formula. So we divide this one by, we multiply this one by 12, I mean, right? So we're simply going to multiply this one by 12 and then we are going to have 0.3. So the mass of carbon 0.3, and then we do the same for hydrogen, right? So we do the same for hydrogen. So for hydrogen, we are having the mass of water. So the mass is 0.45 over the MR, which is equal to 18. So we're simply going to have 0.45 divided by 18, and then we are going to have a 0.025 again. And then from this water molecule, one mole of water, we're having 2 moles of hydrogen atoms, right? So 1 proportionally to 2, and then 0.025 to less, right? So we're simply going to multiply this one by 2, right? Simple proportion, 0.025 over 1 by 2. So this one by 2. So it's a 0.025 by 2. And then we are going to have 0.05, right? So here the mass is equal to 0.05 grams, grams. And then we are left with oxygen. So we are told that the mass of M is equal to 0.43. So here we have 0.05 for hydrogen, and then 0.03 for carbon, right? So we are left with oxygen. So we're simply going to add these two, and then we subtract from this the total mass, right? So this one plus 0.3, and then we subtract from 0.43, and then we are going to have 0.08, right? So we're simply going to have 0.08, right? So we're simply going to have 0.08 grams, right? And then we are going to have our normal procedure of calculating empirical formula, right? So we're dividing with the ARs, right? So here we divide by 12, here by 1, and then here by 16. So it's a 0.3 divided by 12, and then we are back to 0.025, and then here is 0.05, and then here is 0.08 divided by 16, and then we are going to have 0.005, and then we divide with the smallest. So this one is our smallest, right? This one is our smallest. So this one is obviously going to be equal to 1, and then here we have 0.05 divided by 0.005, and then we are going to have 10 right here. And then we do the same for carbon. Carbon we are having 0.025 divided by 0.005, and then we are going to have 5, right? So the empirical formula is C5H10O. So this one is the empirical formula, right? So we have this relationship we say is a molecular formula. Molecular formula, it is the multiple of empirical formula. So empirical formula multiplied by X is equal to the molecular formula. So we are going to multiply this empirical formula by X to have this molecular formula. And also the molecular mass is equal to X by empirical mass. So here we want to determine the value of this X so that we can deduce the molecular formula. So the value of X, we are simply going to have the molecular empirical formula, and then we compare with the molecular formula, then we find the value of X. So we are given that the molecular formula is equal to 86, right? Is equal to 86 here. So we are having 86 being equal to X multiplied by the empirical mass. So here we are having 12 multiplied by 5, and then here we have 1 multiplied by 10, and then here we have 16. So it's 12 by 5 being equal to 60 plus 10 plus 16 being equal to 86, right? So we have 86 here. So X is equal to 1. So this one is a simple linear equation, right? So X is equal to 1, right? So here we're having this empirical formula, right? And then we multiply by X, we are going to have empirical molecular formula, right? So here the empirical formula is C5H10 oxygen multiplied by X, which is equal to 1, is equal to molecular formula. So this one, the molecular formula, is equal to the empirical formula, right? So this one is our molecular formula. So you should be able to define these terms. Empirical formula, the simplest whole number ratios. It is the simplest whole number ratio. It is not just a ratio, simplest whole number ratio. And then molecular formula, it shows all the atoms present in a compound. And then displayed formula, it shows how atoms are bonded. And then we have what you call structural formula, the abbreviated form of displayed formula. We should know the definitions of these formulas by heart. Are we together? And then we are done for the first part. And then we can now simply proceed to the second part. So let me clear here so that we can move to the next part of the question, right? So our part B says explain why solid sodium conducts electricity but a solid sodium chloride doesn't conduct electricity, right? So for sodium chloride we are having first when explaining these physical properties, you need to identify the lattice structure. You need to start by identifying the lattice structure. So this one exhibits a metallic lattice structure, and then this one it exhibits an ionic ionic lattice structure, right? So the forces or the particles in this compound are the ions held by the strong electrostatic force of attraction. And then here we're having the metal cation and a sea of delocalized electrons, right? So here we're having the sea of delocalized electrons, which are mobile and are able to carry the electric current. And then here we're having these ions localized in the lattice structure, right? Here the ions are not mobile; they are localized in the lattice structure, right? So here we're having the electrons, which are free mobile electrons, which are able to conduct electric current. So conduction, it is done by mobility of the conducting particles. So the conducting particles must always be in motion to carry the electric current. So in metals, it is done by electrons, and then in ionic compounds, it is done by the ions. So in the solid phase, the ions are localized in the lattice structure. And then when we are in the liquid phase or in the molten phase, the ions are able to move, right? They are released from the lattice structure, so they are able to move by carrying or conducting the electric current. Are we together? So this is the simple explanation to compare the conduction between solid sodium and sodium chloride, right? And then we now go on to the next part. So the next part says explain why ice is less dense than liquid water, right? So when water cools into solid state, it becomes less dense. So we are required to explain why water becomes less dense as it cools, right? So as it cools, the particles are going to lose their kinetic energy, right? So they are going to lose their kinetic energy. And then this one is the structure of the water molecule, right? So this one is the structure of the water molecule, right? We are having oxygen bonded directly to two hydrogen atoms, right? So oxygen is highly electronegative, meaning to say it has got a tendency of attracting bonding pair of electrons towards itself to attain this partial negative charge. And then this hydrogen atom will attain this partial positive, this one partial positive, and then we are having two lone pairs here, two lone pairs there, right? So this simply means to say water has got the ability to form the hydrogen bonds. So from the principle of the formation of hydrogen bonds, we must have one of the most electronegative elements. We are having nitrogen, we are having fluorine, and then we are having oxygen. So these are the most electronegative elements. So we are having one of the most electronegative elements bonded directly to hydrogen, right? So here we are having our oxygen bonded directly to hydrogen, and it bears a lone pair, right? So this simply means to say we are having the probability for the formation of the hydrogen bonds. So as water cools, it tends to have the more chances or the frequency for the formation of the hydrogen bonds. So water has got the ability to form 4 hydrogen bonds, right? So here it can form one hydrogen bond here, and then one hydrogen bond here, and then we can have another hydrogen bond there, another hydrogen bonds there with other water molecules, right? So as it cools, it has got the ability of forming more hydrogen bonds, right? So here we are going to have the tetrahedral structure. So water is going to form 4 hydrogen bonds, thereby resulting in the formation of a tetrahedral structure, right? So with a bond angle of 109.5 degrees, right? So this structure is more open. This one, the tetrahedral structure, it is more open, and it's got a larger space between the particles. So this one, it will result in the water molecule being less dense compared to the liquid water, which is a bent shape. So the next part says state any 2 uses of nickel. So nickel can be used as a catalyst in the hydrogenation, right? So we can use nickel as a catalyst in the hydrogenation, and then we can also use nickel in electroplating. We can also use nickel in the manufacturing of stainless steel, right? Stainless steel. And then we can also use nickel in the manufacturing of batteries, right? So we have what you call the nickel cadmium battery, right? So these are the uses of nickel. And then the next part says outline the electrolytic purification of nickel. So for the electrolytic purification of nickel, first you need to identify the anode and to have the cathode, right? So like what we did in the purification of copper, we have our impure nickel at the anode, right? At the anode. And then we have the pure nickel at the cathode. Pure nickel at the cathode. And then the electrolyte, we are going to have nickel sulfate with sulfuric acid. Are we together? So here, this one is the anode, this one is the cathode, and then we have the electrolyte. So to have the equation, you must always remember that anode is defined as the electrode where oxidation takes place. So anode, we are going to have oxidation, right? So oxidation, we are simply going to have nickel atoms dissolving to give nickel ions, right? So we are going to have nickel 2 plus 2 electrons. This is oxidation. loss of electrons, right? And then at the cathode, we're going to have reduction, right? So here we're going to have these nickel 2 ions gaining electrons to form the nickel metal. All together, this is the pure nickel metal, and then these are the ions reduced by the gaining of electrons. All together, and then we are also going to have the impurities on the anode, right? This is what we call the anode slag, right? Anode slag, right? So these are the impurities which will then fall on the anode. All together, and we are done with the purification of nickel using electrolytic processes, right? And we are done for number 1, and then we are now moving on to number 2, right? So number 2 says we are given that a Fig 2.1 showing a mass spectrum of an element Q. So this is relative abundance, and we are going also to have mass per charge ratio on our horizontal axis, right? So we are given that the relative isotopic mass of 22, 23, 24, and then this one is the relative abundance defined as the percentage occurrence of the isotope in the natural occurring element, right? So you should be able to define each and every term. You should be able to define each and every term. So here we're given this isotope. So isotopes are defined as atoms of the same element with the same number of protons, same number of electrons, but a different number of neutrons, right? So this one is the definition of an isotope. We're going to have the same number of protons, same number of electrons, but different number of neutrons. This simply means to say we are going to have a different mass number, or what you call the nucleon number, right? So when we did the subatomic particles, we said that the mass of an element is determined by the nucleus. So in the nucleus, we're going to have protons and the neutrons, right? These two, they are going to constitute the mass, right? So the mass of a proton is equal to 1 unit, and then the mass of a neutron is also going to be equal to 1 unit. And then the electrons, they've got a negligible mass of 1 over 1840. So they are not going to be included when calculating the mass of an isotope of an atom. Why? Because they've got a negligible mass of 1 over 1840. Are we together? So you must always understand the subatomic particles inside out. You must know the subatomic particles inside out, right? So here we want to understand this mass spectrum, right? So we're given the abundance, and then we have this mass per charge ratio, right? So they use the formula of the species responsible for the peak at the mass per charge ratio 24, right? So we're given that we're having element Q, right? So the species, we're going to have Q, right? This one is our Q, and then they are going to be ionized. So you must know the mass spectrometer. They're going to be vaporized. We're going to be ionized. We're going to have deflection, acceleration. You should know the mass spectrometer. You must know the steps of the mass spectrometer, right? So you're going to have Q, and then this one is the charge. They're going to be positively charged ions, right? And then we're going to have the isotopic mass, which is equal to 24, right? So this one is the species, right? And then we go on to the next part. So the next part says given that the peak it's the mass per charge ratio 23 is equal to 6 centimeters. So this peak is equal to 6 centimeters, right? So calculate the peak height. It's a mass per charge ratio 24. So we want to have the height, right? So let me clear here. So here 60% the abundance is got a height of 6 centimeters, right? And then here we want to have 20%. So 20 is equal to less, right? So we're going to have 20 over 60 multiplied by 6. So this one we cancel out, and then this one and this one we also cancel out, and then we are going to be left with 2. So it's going to be 2 centimeters. Are we together? And then we go to the next equation. So the next equation says calculate the relative atomic mass of Q. So for us to have the relative atomic mass of Q, AR, we're simply going to have the isotopic mass times abundance. So this one by this one, right, for each and every isotope, right? So this one is 22 by 20. So it's 22 by 20. And then we add, the next one is 23 by 60. So it's 23 by 60. And then we add again. This one is 24 by 20 again, right? So it's 24 by 20. And then we divide by the total abundance, right? So the total abundance, we're having 20 here, we're having 60, and then 20 here. So it's 20 by 20, 40 plus 60 to give us 100%, right? So we're going to have 100% here, right? So we're simply going to punch this straight to our calculator. We are going to punch this one straight to our calculator, right? So we're having 22 multiplied by 20, and then we're going to add 23 multiplied by 60, and then also we're going to add 24 multiplied by 20, and then we're going to divide by 100, and then we are going to have 20, 23, and we are done, right? So the relative atomic mass is equal to 23, right? And then we go on to the next equation. So the next question says, state the group number of the periodic table to which a cube belongs. So we go to the group to the periodic table, right? So let us have the periodic table so that we can identify the element with a mass of 23, right? So you should know the first elements by heart, right? So here the periodic table is not given, so obviously it is sodium, right? With the AR of this one, it is obviously going to be sodium, right? This one is sodium, but I just wanted to show you how we are going to deduce, right? So I believe you guys have done the nuclear notation. So nuclear notation, this one is the atomic mass, then this one is the proton or the atomic number, right? The number of protons or the atomic number. Are we together? And then describe and explain how the first ionization energy of Q would compare to that one of lithium. So we want to compare the first ionization energy of sodium to that one of lithium. So ionization energy is defined as the energy required to remove one more of electron from one more of a gaseous atom to form one more of a gaseous unipositive ion. So this one is the first. So we're going to form one more of a gaseous unipositive. It's unipositive ion, right? So we are going to have this sodium is a gas, going to have the sodium ion, right? And then here we're going to have the electron. Are we together? So this is the equation for the first ionization energy of sodium. So we are required to compare the first ionization of energy of sodium to that one of lithium, right? So we are going to illustrate this one using the diagram. So this one is our lithium, which is smaller, and then we're having this positive charge in the nucleus, the nuclear charge, right? And then here for sodium, we are going to have this inner shell, and then we are going to have this outer shell, right? So let us use the O level information, right? So the electronic configuration for sodium is 28281, right? So we're simply going to have these two shells, and then we are going to have this inner shell, the outer shell, the valence shell, right? And then here for lithium is 221, right? So here we're going to have this shell, and then we're going to have this, and then we're going to have this. So let me highlight again. So we're going to have this positive charge, and then this outer shell, and then you have this outer electron, and then here we have this outer electron, right? So here, as you can see, we're going to have increased distance from the nucleus to the valence shell, right? And then here we're going to have reduced distance between these two. So meaning to say the force of attraction between this positive charge and this electron negative cloud is going to be stronger, and then here the forces are going to be reduced. And then we are also having these inner shells which are shielding the effective nuclear charge from reaching this external or exterior environment, which is the valence shell, right? So here we are going to have more pronounced shielding compared to here. So here we have more shielding compared to lithium, meaning to say the electron in this shell is lessly held by the nuclear charge, and it is easier to lose compared to this one. So here we're going to have low ionization energy, and then here we're going to have high ionization energy. Are we together? So this is the simplest way to understand these trends in ionization energies. Are we together? Are we together, guys? So we are going to have sodium having a lower ionization energy compared to that one of lithium, right? And then we are done, and then we are now moving on to the next part. So the next part says state any two types of catalysis. So we have what you call the homogeneous catalysis, and then we have what you call the heterogeneous catalysis, right? So when you say it's a homogeneous catalysis, we are simply saying that the reactants and the catalyst are in the same phase. They can be in the same phase, they can be in the same liquid phase, they can be all gases, they can be all solids, right? They are in the same phase. And then when we say it's heterogeneous catalysis, we are saying that the reactants and the catalyst are in different phases. It's either the reactants are in the gaseous phase and the catalyst is in the solid phase, which is more common, right? Example of a reaction with a homogeneous catalysis, we're going to have the reaction between peroxide disulfate ions. These are the peroxide disulfate ions with the iodine ion. So this is the reaction. So these are negatively charged. So we're going to have repulsion between these two. So we're going to use what you call the ion 2 ion 3 system to catalyze this reaction, right? So we're going to have ion 2 ion 3 system. So they are in the same phase. So this is what we call homogeneous catalysis. And then for heterogeneous, we are going to have the Haber process. We can have the conduct process, right? All the most of the industrial processes, they are heterogeneous catalysis, right? So for the Haber process, we're going to have nitrogen and hydrogen as the reactants, and then we're going to have powdered ion as the catalyst. So at times it can be examined to explain why ion is said to be powdered. So it is powdered to increase the surface area, right? To increase the surface area, and then we're going to have more contact points, right? So you should always understand this. We are going to have more contact points. Are we together? So catalysis, we are going to have the increment in the speed of the rate of a reaction, right? So this the reaction is going to be increased by providing an alternative route with lower activation energy. Activation energy defined as the minimum amount of energy required to start a chemical reaction. Are we together? So these are the principles in reaction kinetics, right? So let us dive to the next part, to the next equation. So the next question says, describe the ion catalysis between hydrogen and nitrogen. So this is what he said. We're going to have the reaction in the upper process, right? So here it is heterogeneous catalysis, right? So heterogeneous catalysis, we're having this one is the gas, this one is the gas, and then this one is the solid. So we're going to have the adsorption of these gases, hydrogen and nitrogen, on the surface of the catalyst, which is our powdered iron, right? So these gases, they're going to adsorb on the surface of the catalyst, and then we are going to have the weakening of the bonds as they are going to react, right? So bonds are going to be weakened, right? So we're going to have the weakening of the bonds, and then afterwards we're going to have what you call the product dissolved, right? So the product, they're going to dissolve, what you call detachment of the reactants from the active site. So thereby we're going to have the freeing of active sites for another reactant, right? Are we together? So here we are simply going to have adsorption, and then bonds weakening, and then we are going to have the removal of the products, what you call the desorption of the products, right? And then we are going to have the freeing of the active sites on the catalyst, right? So active site, we normally talk of active site when dealing with A level, with biology, I mean, when we discuss of enzymes. So enzymes are defined as biological catalysts, so they are catalysts in the biological processes, right? So you must always highlight that. And then we go on to the next part, which is number C. So number C says a buffer was prepared by mixing 2 grams of ammonium nitrate and 75 cubic centimeters of 0.01 cubic moles per cubic decimeter ammonia, and then we are given the Kb, right? So the Kb is equal to Kb of ammonia is equal to 1.75 by 10 to the negative 5, right? So a buffer solution is a solution which resists change. It resists change in pH on addition of small amounts of either an acid or a base. So we have 2 types of buffers. We have an acidic and a basic buffer, right? So in acidic buffer, we are going to have a weak acid and a sodium salt of that acid, right? A sodium salt of that acid. And then for a basic buffer, we are going to have an ammonia, a weak base, which is ammonia, right? Normal ammonia, I mean. And then we are going to have an ammonium salt of that weak base, right? So normally we are going to have an ammonium salt, right? So the first part says name the type of the buffer. So this one is obviously a basic buffer, right? So we are going to have a basic buffer, right? We are having a weak base, and then a salt of the weak base. So here the weak base is ammonia, and then the salt is ammonium nitrate. Are we together? And then we are required to calculate the pH, right? So for us to have the pH, we're simply going to use what you call the Henderson-Hasselbalch equation, right? So this one we are going to have a basic buffer. So we are going to use the formula is POH is equal to PKB plus log salt over the base, right? And we are done, right? So we're simply going to substitute. So our POH is equal to PKB. So our KB is given here, so it's negative log KB 1.75 by 10 to the negative 5, and then plus log our salt. So here we're given the mass, so we want to have the concentration of the salt, right? So we're given the mass, so N is equal to M over MR, right? So N, so here we have 2 grams of ammonium nitrate. We're simply going to add these ARs. So here we're going to have 14, and then here we are going to have 4, and then here we're having 14. Then here is 16 by 3, right? So we're simply going to punch this through to our calculator, and then we are going to have so we're going to have 16. So it's 16 by 3 plus 14 plus 14 plus 4, and then we are going to have 80, right? So here is divided by 80, so N is equal to this one, and then it's 82 divided by 80 is 2 divided by 80, and then we are simply going to have 0, N being equal to 0.025. So these are the number of moles, right? And then we are going to divide so that we can have the concentration. So N is equal to CV, so we want C, so it's N over V is equal to C, right? So here we're given this one is the volume, right? So here is 0.025 over the volume. So the volume is in cubic centimeters, so it's 75 over 1000 to convert it into cubic decimeters, right? This one is going to be 0.075, right? So this one is 0.75. So we're simply going to divide 0.025 divided by 0.075, and then we are going to have concentration being equal to 0.333 is a recurring decimal, so it's moles per cubic decimeter, right? So this one is the concentration of the salt, right? And then the concentration of the base we are given is 0.01, right? So we're simply going to substitute. So here it's let us store this one as A, right? So it's log the concentration of the salt, which is this one, we have stored as A, so alpha A over the concentration of the base, which is equal to 0.01, and then we are going to have this one. So we have our answer is 1.522878745, right? So this one is the value for this expression, and then we want to have pKb. So pKb, we're simply going to let's do this one as a store N, right? So pKb is negative log of our kb. So our kb is equal to 1.75 by 10 to the negative 5, and then we are going to have 4. So we are going to add this one with 4.756961951, so plus alpha A, and then we are going to have 6.25984067 is our pOH, and then the question requires us to have pH, right? So we're simply going to go back to the relationship. So the relationship says pH plus pOH is equal to 14. So here we want to have pH, so it's pH is equal to 14 minus pOH. So this one is our pOH. We're simply going to subtract this one from 14. So minus 14. Then we are going to have 7.7200. So pH is equal to 7.720159303. And then at 2 decimal places, so it's pH is equal to 7.72 to 2 decimal places, right? And we are done. So this is the value of the pH to 2 decimal places, right? And then we now proceed to the next part. So we are done with number 2, and we are now moving on to number 3, right? Number 3 says define the term electronic configuration, right? So electronic configuration is defined as the arrangement of electrons in their electric shells, right? Of electrons in their electric shells, right? So we have what you call the shells, you have the subshells, we have the orbitals. So you should be able to define these terms, right? So a shell is defined as a group of orbitals with the same principal number, right? So a shell, these are the groups, a group of electron orbitals with the same principal quantum number. So quantum number simply means to say energy level, right? So we are having n being equal to 1, 2, 3, and etc., right? So this is definition of a shell. And then we go on to define what you call the subshell. So a subshell is defined as a subdivision of a shell characterized by the quantum number, right? So we have what you call the S, P, G, and then F, right? So these are the subshell, right? So the definition of a subshell, we're saying that we're having a subdivision of a shell characterized by the quantum number, right? And then we lastly go on to the orbital. Orbital defined as the region in space where we're having the highest probability of finding an electron, right? So in the orbitals, we're having the regions where we're having the maximum probability of finding an energy carrying electron, right? So these are the definitions. So you should familiarize yourself with these definitions, right? So the next part of the question says write the electronic configuration of the oxide ion, right? So first we need to identify the position of oxygen on the periodic table, right? So oxygen, it is on number 8, right? So it's O8, and then we have 16 here, the mass number. This is the nuclide notation, right? So we want to write the electronic configuration of the oxygen atom before we go on to the oxide ion, right? So for the oxygen atom, we're simply going to have 1s2, 2s2, and then 2p4, right? So this one is the electronic configuration of the atom. And then here we're having these 2 minus, these 2 indicating the number of electron, and then this negative charge indicating that we have got an increment in the negative charge, right? So this simply means to say we have gained extra 2 electrons. So here we're simply going to add 2 electrons, right? So this the resultant electronic configuration is 1s2, 2s2, and then 2p6, and we are done, right? So this is the electronic configuration of the oxide ion, right? And then we go on to the next equation. So the next equation says, using the valence shell electron pair repulsion theory, deduce the shape and the bond angle of the carbonate ion, right? So the carbonate, these are very easy polyvalent ions. They are very easy to deduce the shape, right? So we're simply going to have this carbonate, right? So we are having these 2 minus. So these 2 minus indicates that we are having 2 oxygen atoms coming to the bonding system with already 7 electrons, right? So they've got gained, each atom has got gained an electron from the reacting system, right? So we have one single bond here because the oxygen atom has got 7 electrons. And then here we also have another oxygen atom with one single bond here, right? And then we have the double bond for the remaining oxygen atom, and we are done, right? So the maximum number of bonds around the central carbon atom must be always equal to 4. So here it's 1, 2, 3, 4. So carbon has attained the maximum number of bonds, right? And then here we're simply going to deduce the shape. So this one is a trigonal planar with a bond angle of 120 degrees, right? So it's a trigonal planar with a bond angle of 120 degrees, right? So this one is the shape of the carbonate ion. Are we together? So these polyvalent ions, they are very easy to deduce the shape. You simply use this chart to have the number of oxygen atom coming to the bonding system with 7 electrons. Are we together? And then we go on to the next shape, which is hydrazine. So hydrazine, we're having this shape, having nitrogen to nitrogen single bond, and then we're left with this one hydrogen atom, this one hydrogen atom, this one. So the number of electrons in the outermost shell for nitrogen, we're having 5. Nitrogen is in group 5, right? So this simply means to say we're having 5 electrons in the valence shell. So here we've got used 1, 2, 3, and then we are left with 2, right? So we are left with 2 electrons, which is 1 lone pair of electron, and then this applied to this nitrogen atom again. So we're around each nitrogen atom, around this nitrogen atom, we are having 1, 2, 3 bonds, and then 1 lone pair. So 3 bonding pair, 1 lone pair. The shape is equal to trigonal pyramid. Pyramid with a bond angle of 107 degrees, right? So this one is the bond angle of each nitrogen atom in hydrazine, right? So this is how we are going to do when deducing the shapes of these elements, right? And then we proceed to the next part, which is part number C. So part number C says a 3-gram mixture of sodium chloride and millimule was dissolved in 100 cubic centimeter distilled water, and then it was filtered, right? So here, these are the physical separations we did in O level, right? So whenever we are mixing millimule and sodium chloride is soluble in ionic compounds, are soluble in water, right? Through ion dipole solvation, right? So here we're having sodium chloride being soluble, and then here we're having this millimule, which is going to form the residue, right? So the mixture was said to be filtered here, right? And then we are having 25% of the filtrate. So this millimule will absorb water, right? You know that, right? So millimule is going to absorb some of the water, and then we are going to be left with the filtrate, which contains sodium chloride, right? So from the general social life, you know that if you are going to mix water with millimule is going to absorb a certain amount of water, right? So here we are told that we are having 25 cubic centimeter of the filtrate, right? And then the filtrate was reacted with excess silver nitrate, and then we are going to have a precipitate of silver chloride, and then it weighs 5.89 grams, right? And then we are required to calculate the mass of sodium chloride in the sample, right? So here we are simply going to have the back titration, right? We are simply going to have the equation for the formation of this silver chloride. So we are having the silver ion, right? So here we're having this silver ion plus the chloride ion to have the silver chloride. Are we together? So here we want to have the number of moles. Here we have one more. So stoichiometrically the number of moles are equal, right? So we want to calculate the number of moles of this silver chloride using the mass here, right? So N is equal to mass over MR. So we want to have the MR of silver chloride. So we're simply going to have silver, the mass of silver plus the mass of of chlorine. So this one we are simply going to have 143.5, right? So N is equal to 5.89, the mass, right? Here the mass divided by the MR, which is equal to 143.5, and then N is equal to, so we're simply going to punch this straight to our calculator, right? So it's 5.89 divided by 143.5, and then we are going to have 0.04104529.6, right? So these are the number of moles in the silver chloride. So the number of moles of silver chloride are the same as the number of moles of the chloride ion, is the same as the number of moles of the silver ion. So here we are mainly focused with this chloride ion. So the chloride ion is coming from the sodium chloride. So sodium chloride is going to dissolve by liberating the sodium ion. So this one is the sodium ion plus the chloride ion. So here we are having equal stoichiometric ratios, one more here and then one more here, meaning to say the number of moles here are the same as the number of moles there, right? So here the number of moles of this sodium chloride are the same as the number of moles of this chloride ion, right? So we're simply going to have N or sodium chloride being equal to 0.0, this one 0.04104529.6, right? And then N is equal to mass over MR, the chief equation in stoichiometry. So we want to have M, the mass, right? So we are required to have the mass of sodium chloride, right? So we want to have M. So it's N multiplied by MR is equal to mass. So the MR of sodium chloride, this one is 58.5, right, from the periodic. So we simply add 23 from sodium plus 35.5 from chlorine, right? So here N 0.04104529.6 multiplied by MR, which is equal to 58.5. And then we are going to have the value of M. So we're simply going straight to our calculator, and then we multiply this one by 5.8.5, and then we are going to have 2.401149.826 grams being equal to the mass. And then to 2 decimal places, we're going to have 2.40 grams being equal to the mass of our sodium chloride, right? And then the next part of the question requires us to have the percentage purity. So percentage purity is the mass of pure sample of the over the mass of impure sample multiplied by 100. So the mass of the pure sample is equal to 2.40 over the mass of impure. So the mass of the impure sample we're having, this one the mass of the mixture, right? And then we're simply going to have over 3 multiplied by 100, right? So we're simply going to punch this one straight to our calculator, divided by 3 multiplied by 100, and then we are going to have 80. So it's 80.03832753, right? So here to the nearest 1 decimal place is 0.0%, right? So this one is the percentage, this one is the percentage purity, and we are done, right? So you should always familiarize yourself with this kind of questions, right? You should always familiarize yourself with this kind of questions, right? And then we are now moving on to the next part. So for the next part says steam reacts with carbon to give hydrogen and carbon monoxide at a pressure of 12 atmospheres, and then at equilibrium we're having 60% of steam yet reacted, right? So 60% of steam had reacted at equilibrium. So we are required to write the chemical equation for the reaction. So we are having steam. So let me highlight this one. So it's steam in the gaseous phase reacting with carbon. So we're having this one in the solid phase to give hydrogen. So this one in the gaseous phase plus carbon monoxide in the gaseous phase. And then to balance this equation, So the equation is already balanced, right? So here we are told that we are having the reaction in equilibrium, meaning to say this one is a reversible reaction, right? So you need also to highlight this one, that it is a reversible reaction. It is a reaction which proceeds in either direction, right? And then we are done. So we are now moving on to the next part. So the next part says calculate the number of moles of each component at equilibrium, right? So here we are having, so this one is not included in equilibrium because it is a solid, right? And then here we're having 1 minus x, and then here is x, and then here is x. This one is the initial. So here we are told that 60% of steam had reacted, so we are going to be left with 40%, right? So here let us assume that this one we're having one more of each of the reactant components in the product, right? So we are saying that we are going to have 1 minus 60%, which is equal to 0.6, to give us 0.4 moles, right? So here we're having 0.4. So we are saying that 1 minus x is equal to 0.4, and then we want to have the value of x. So this one is a simple linear equation, right? is equal to x, and then 0.6 is equal to x. So here is 0.6, and then here is 0.6. So these are the moles at equilibrium, right? So these are the moles at equilibrium. So here we're having 0.4 moles at equilibrium. This one 0.6, this one 0.6, right? So these are the number of moles of each component at equilibrium, right? And then the partial pressure of each component. So for the partial pressure, we're starting by having the total number of moles. So the total gas moles, we're simply going to have 0.4 plus 0.6 plus 0.6. And then we are going to have 1.6 moles in total. And then the partial pressure of each gas, we are simply going to have the number of moles of that gas. So let us start with steam, right? So steam, the partial pressure of steam, we're simply going to have the number of moles over the total number of moles multiplied by the total pressure, which is equal to 12, right? So here we multiply by 12, and then we are now going straight to our calculator. So is 12 is 0.4 divided by 1.6 multiplied by 12, and then we are going to have 3. So it's 3 atms, right? And then we do the same, the partial pressure of hydrogen. So hydrogen 0.6, right? So the partial pressure of hydrogen, we're simply going to have 0.6 over 1.6 multiplied by 12, and then we are simply going to straight to our calculator, right? So here is 0.6, and then we are going to have 4.5. So it's 4.5 atm, and then we do the same for carbon monoxide, right? So for carbon monoxide, we are simply going to have 0.6 again over 1.6 by 12, and then we are going to have 4.5 atm, right? So these are the partial pressure. These are the partial pressures of each of these gases at equilibrium, right? And then we are required to have Kp. We are required to have Kp. So for Kp, we are simply going to have this. So let me clear here. So Kp expression, we are having the products, the partial pressures of the products over that one of the reactants. So here these are the products over this one of the reactants, right? So we are having the partial pressure. So the partial pressure of hydrogen raised to the appropriate number, which is 1, appropriate integer, over the partial pressure of carbon monoxide all over the partial pressure of steam, right? So we are having Kp being equal to the partial pressure of hydrogen is equal to 4.5, and that one of carbon monoxide 4.5. So we are having 4.5 by 4.5 over the partial pressure of steam. So the partial pressure of steam is equal to 3, right? So here we are having over 3, and then we are simply going to punch this one. So it's 4.5 by 4.5 all over 3, and then we are going to have 6.75, and then the units of Kp. So here we're having atm by atm from this numerator over atm. So this one and this one is going to cancel out, and then we are going to be left with atm here. So this one is the value of our Kp, and we are done, right? So let us move on to the next part of the equation. So we are now moving on to section B, right?